Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. Last class we have discussed regarding the stability and bifurcation of the nonlinear systems. Two different type of bifurcations we have studied or we have discussed. So, one is static bifurcation and other one is dynamic bifurcation. So, today class we will deliberate more on the static and dynamic bifurcations along with stability analysis, and we have taken the example of these Duffing equations, and also to study whether a system is stable or not, we should also know the numerical methods to solve the differential equations. Already we have discussed this thing many times in this course. So, for example, so you have to use this Runge-Kutta fourth order method. Either you can use the codes available in different software packages like in MATLAB. You can use this ODE 4.5, if you have stiff equation then you can ODE 2.3, or other softwares also you can use for different types of nonlinear equation solvers. In case of you are using this Runge-Kutta method, you can write your own code also. So, where you can use in this fourth order Runge-Kutta method. So, you can write this solution in this form yk plus 1 equal to yk plus k1 plus 2 k2 plus 2 k3 plus k4 by 6, where k1 equal to h f xk yk, k2 equal to h f xk plus h by 2 yk plus k1 by 2, k3 equal to h f xk plus h by 2 yk plus k by 2, and k4 equal to h f x k plus h by 2 y k plus k 3 by 2, where h is the time interval. So, if you take this time interval very small, your accuracy of the solution will be more, or it will be more accurate solution you can get. So, after choosing this k and the initial condition, for example, so you can start with a initial condition. Taking this initial condition yk, you can find the next yk plus 1, what will be the response after the time interval h. So, in that way you can write down this code of your own and you can solve this equation. Previously also we have taken these perturbation methods. So, by using the perturbation methods you can get the reduced equations. Those reduced equations also you can use this Runge-Kutta method, because those reduced equations are first order equation. So, for steady state, as they will not be function of time, directly you can get a set of algebraic or transcendental equations which you can solve. Otherwise, you can use this Runge-Kutta method to solve these first order differential equations to find the solution. If you have a second order differential equation, for example, x double dot plus x equal to 0. So, in that case you know the closed form solution of this thing, which can be written as a sin t, here omega n square equal to 1. So, omega n square. So, this equation can be written in this form x double dot plus omega n square x equal to 0. So, this is the equation of a spring mass system, where this omega n equal to root over omega n square equal to k by m, or omega n equal to root over k by m, but its solution already you know, it is equal to x equal to a sin omega n t plus phi. So, a sin omega n t plus phi. Here A and phi depends on the initial condition. So, you can take the initial displacement and initial velocity as initial conditions and you can find x. So, here to write down the code in MATLAB. So, you have to initially you just assume let your y1 equal to x and dy1 equal to x dot. Similarly, y2 will be equal to x dot. So, dy2 equal to x double dot, but your x double dot is nothing but in this case equal to minus x. So, you can write your equation in this form, that is dy1 in the function file you can write. So, here the code is written below. So, you can see the code. So, in the function file it is written, for example. So, you have taken two equations. So, initially you just initialize with 0. So, dy equal to 0s to 1. So, this is 2 row and 1 column. So, your dy1 equal to y2 and dy2 equal to minus omega square y1. So, this is the function file, and in the main file you can call the function to find. So, this is the main file. So, here you have to decide or you just declare the time space t equal to line space 0 to 100. So, if you have to do it up to 100 with 5000 divisions it has been taken. Initial a0 equal to taken 2. So, t span minimum time and maximum time you can specify. So, y0 initial condition, for example, y0 equal to a0 0, that means initial displacement equal to a0 and initial velocity equal to 0. So, you can take different things also. For example, if the system is subjected to some impulse type of forcing, then the displacement you can take 0, but the velocity will be equal to f delta t by m. You can find the initial velocity and you can put it. So, depending on the application, so you have to choose this initial condition. Here by taking this initial condition y0 equal to a0 0 you can take. So, you can write this OD ty equal to OD 45 at the rate tf1. So, you just see this tf1 is the function file name. So, tf1 t span y0 you can write. So, there are some other options also available. So, you can check, this is the simplest one you can put. You can write in, for example, in figure 1 let you plot the time response, in figure 2 let you plot the phase portrait. In figure 1, so plot t y colon 1. So, that means in y, so you are storing the first column you are storing this y, and in second column you are storing this y dot. That means, you are storing this x and x dot, that is displacement and velocity in these two columns. The first column of y will store the displacement, the second column is storing the velocity. So, when you are plotting this phase portrait, that time you can plot y1 comma y2. So, you can see here, then this y level. So, you can put plot t comma y colon 1. So, that means give you the first column. So, all the first column, that is displacement. So, this plot you can see displacement versus time. So, already you are familiar with the solution y equal to y0 sin omega t. Here by putting this t equal to 0, displacement equal to 2. So, it will start from, so you have to put that equation. So, a0 equal to a sin omega t. So, two way you can write this. You just see the closed form solution, either you can write it in this way or you can write x equal to a sin omega n t. So, if you want to compare your result with respect to the analytical solution, this way you can do also. So, b cos omega n t. So, at t equal to 0, so we have taken x equal to a 0. So, a 0 equal to, so a 0 equal to b. Now, you can put x dot. So, x dot equal to a omega n cos omega n t plus, for b it can be a 0. So, for cos differentiation equal to a 0 omega n sin omega n t. So, at t equal to 0, so as it is equal to 0 you are taking. So, 0 will be equal to a omega n. So, a omega n equal to 0. So, as omega n is not 0, so a equal to 0. So, the solution becomes x equal to b cos omega n t, b cos omega n t, where b equal to a 0. So, this becomes a 0 cos omega n t. The solution becomes a 0 cos omega n t. So, you can compare this thing with the solution what you have obtained by using this Runge-Kutta method. Here you just see it has been plotted from 90, that is why you have not seen at a t equal to 0. So, what is the values by changing this axis property. So, it has been set from 90 to 100 to the response to be periodic. So, here also the phase portrait is not plotted for the whole range 0 to 100. So, it has been plotted from only 90 to 100. So, you can choose. So, for example, here you just see the plot command. So, plot y 1500 to 2000. So, you have taken only the data available from 1500 to 2000, column 1, comma y 1500 to 2000, column 2, that is this is displacement versus this velocity we are plotting. So, you can label this x level as y level as velocity, x level as displacement, then title phase portrait. So, this is the phase portrait we have seen. So, now as an assignment, so you can check by using this way. So, you can check the doping equation also. So, in this doping equation, if you want to find the response, so in that case only this function has to change. Here the first one will remain same also. Your doping equation let you write the doping equation in this form, that is x double dot plus omega n square x plus alpha x cube plus 2 zeta or 2 mu x dot, you can put 2 mu x dot will be equal to f sin omega t or f cos omega t, let us put, you can put f sin or f cos omega t. So, in this case, so your first equation will remain same, second equation is nothing but, so this part will be replaced by x double dot. So, x double dot in this case equal to x double dot equal to f cos omega t minus omega n square x minus alpha x cube minus 2 mu x dot. Here, so you have to substitute, this is equal to f cos omega t minus omega n square. So, for x, so x equal to your y1, so minus alpha x cube, so this becomes y1 whole cube, you just see y1 whole cube you can put whole cube. So, minus 2 mu for x dot, so it can be, so it is equal to y2. So, this way you can write your function 2. So, this function 2 can be written dy2 can be replaced by this one, and you can use this same ODE45 function to find the different solution for a doping equation. So, different solution for doping equation. So, you can verify for different value of different coefficients, the response may be periodic, sometimes it will be periodic. So, in case of the periodic, if you plot the displacement versus x dot, so in case of periodic, so you can see the phase portrait will be, so the phase portrait will be a closed solution. So, in case of for some other value of the system parameter, so you can see the phase portrait may contain 2 loops. So, for some other value, if you go on changing your system parameter, for example, if you go on changing this value of forcing f, so amplitude of forcing parameter if you go on changing, so you can see it will go on. So, this is periodic, this is 2 periodic, then you can have 4 periodic. So, in case of 4 periodic, so there will be 4 loops. So, here you just see this is loop 1, this is loop 2. Similarly, you can have 4 loops. So, for example, this is 1, this is the second one, another one, and this one. So, you can have 4 loops. So, this is one loop, this is the second loop, this is the third loop, and the whole thing is itself is a loop. So, that is 4 loops. So, by changing the system parameter, if you write the equation particularly, so if you write this equation in this form, for example, let me write and you can verify this thing. So, the equation if it is written x double dot plus delta x dot plus alpha x, let me write this way, plus beta x q equal to gamma cos omega t. So, if you take the value, for example, take the value of alpha equal to minus 1, then beta equal to plus 1, beta equal to plus 1, then delta equal to damping delta equal to, let you take equal to 0.3. So, damping equal to 0.3, then omega, let us take omega equal to 1.2, and initial condition let me take x 0 equal to 1 and x dot 0 equal to 0, displacement equal to 1 and velocity equal to 0. So, if you take these parameters, so for you can see for gamma equal to 0, you can see the response, or gamma equal to 0.2, gamma equal to 0 is the free vibration response. So, gamma equal to 0.2 if you put, then you can check that the response is periodic. The response is periodic like this thing. So, you can get a response. So, if you take this gamma equal to 0.28, for example 0.28, so you can find this is 2 periodic. Similarly, if you take gamma equal to, for example, you just take gamma equal to 0.29, gamma equal to 0.29. So, it is 4 periodic, and if you take higher value of gamma, for example, you just take gamma equal to 0.5. So, you verify this thing, gamma equal to 0.5. So, the response will be chaotic. Chaotic means, so it contains many harmonic terms, more than 16 times or more than around 30 harmonic terms it will contain. So, the response is chaotic. So, the chaotic response are deterministic response, but it will contain many harmonics and you cannot distinguish from the time response and from the phase portrait. So, we can easily check that the response to be chaotic. This chaotic response, in case of chaotic response, it depends on the initial condition. By changing this initial condition, so you can check that, so you can get different type of attractors. In one case, for example, by taking 1 0, you will get one type of attractor. By changing that initial condition, you can verify that you are getting different other attractor. The attractor will not be same. So, you can verify this thing. Another conditions also you can take and check. So, if alpha equal to 1, in this case, in this particular case, you just see alpha you have taken to be minus 1. So, in this case, you have taken alpha equal to minus 1. Particularly, if you see this equation x double dot minus alpha x. So, you just see the system is unstable. So, in case of a linear system, so x double dot minus alpha x, alpha is positive, or you just take this plus and now alpha is negative. So, if alpha is negative plus delta x dot, in linear case actually the system to be, the linear case the system is unstable, but by adding this, by adding this cubic nonlinearity and applying some force, so you can see it yields to different type of responses. We now understand that in addition to fixed point response, so there is other type of responses also available in our system. So, they are periodic response. This periodic may be single frequency, it may be multi frequency. So, in case of single frequency, this is single period you got. So, in case of 2 frequency, so you can get this type of 2 lobes, in case of 4 frequency 4 lobes. So, in all these cases if you check carefully, so the frequency ratio are in the form of integer numbers. So, this let it is omega 2 and omega 1. So, omega 2 by omega 1 must be in the form of integer, but if they are irrational number. So, let us take some irrational number. For example, one frequency omega 1 equal to 2 and other frequency omega 2 equal to root 2. Root 2 times 2, 2 root 2. So, in that case you can verify that the phase portrait will no longer be similar to this, but it will be similar to a torus. So, it will be similar to a torus. So, what is a torus? So, you can check in case of a torus. So, you have 2 circles which are connected by, so connected by this. So, this way they will be connected. So, this is torus. So, we will study more regarding this torus when we will discuss regarding this quasi periodic response. So, now let us again come back. So, these are the different type of response you can get. So, given a differential equation, so now you can use this ODE 45 from the MATLAB to get different type of response. So, this response you can try and you can find. So, let us come back to, so again, so let us briefly again check that if we have a equation. So, we can study the stability of that equation by studying or by finding the trace and determinant also. So, this part already we have discussed. So, now let us see few definitions. So, one is this hyperbolic fixed point. So, we know now, so given an equation, for example, let we have a equation x dot equal to f x. So, this is the given equation and we want to study the stability of this equation. So, in that case, so we know the equilibrium point or the fixed point. So, when the equilibrium point is said to be, so there are several definitions are there. So, one is hyperbolic fixed point when all the eigenvalues of A. So, we can find this d f x. So, we can find this d f x. This d f x can be written as A x. So, this A matrix is the Jacobian matrix. So, when all the eigenvalue of the Jacobian matrix have non-zero real parts, it is called or it is known as hyperbolic fixed point. So, already we have discussed regarding this eigenvalue and we have seen. So, if all the eigenvalues, so if you plot, this is the real part of the eigenvalues, this is the imaginary part. So, you take all the eigenvalues for different system parameter. If the eigenvalues are in the left hand side of the S plane, so if they are on the left hand side of the S plane, then the system is stable. Here the hyperbolic fixed points. So, when all the eigenvalues of A have non-zero real parts. So, it may be in the right hand side or in the left hand side of the S plane, but if it is non-zero real part, then they are known as hyperbolic fixed point. So, think if all the eigenvalues of A have negative real parts, if all the eigenvalues of A, so they are negative real parts, so then it is known as sink. So, that means, so if they have negative real part, that means the system is stable. So, if the system is stable, so it is known as sink. The sink may be stable focus if it has non-zero imaginary parts and if it is node, if it contains only real eigenvalues which are negative. So, out of all these eigenvalue, if all the eigenvalues are only, so it has 0 imaginary parts, then we can get node. So, if they are complex conjugate, then we will get oscillatory motion. So, that time it will be, so it may have non-zero imaginary part. So, in that case we will get focus. So, it is known as stable focus. and in case of only node, so we will get stable node if it contains, so if it contain only the real part, if the imaginary part is 0. So we can have two options, either imaginary part is 0. So, if imaginary part is 0, then we will have the stable node. If imaginary part is 0, then we can have stable node. So, this is imaginary part 0. So, if imaginary part is there, then we can have, if imaginary part is there, then we can have stable focus. So, here, so it will spiral, actually it will spiral down to get the response. So, already we have plotted those things and we will see it again. So, then source, if one or more of the eigenvalues of A have positive real parts, so then some of the roots or some of the eigenvalues will be in the right hand side of the S plane. So, in that case it is known as source. So, we will have source. So, if one or more of the eigenvalue of A have positive real parts, here the system is unstable and may be unstable focus or unstable node. So, if it is a complex number, that is non-zero imaginary part, that case we will get focus, unstable focus, and if it is 0 imaginary part, but it is in the right hand side, then it will be unstable node. Saddle point. So, when some of the eigenvalues have positive real part and some other have negative real part. So, that means, so it is in both the side of the S plane. So, then we can tell it is a saddle node, saddle point, this is saddle point. So, in case of saddle point, equilibrium point can be told to be saddle point if some of the eigenvalues have positive real parts, while the rest of the eigenvalues have negative real parts. Marginally stable if some of the eigenvalues have negative real parts, while the rest of the negative eigenvalues have 0 real part. It is marginally stable. So, if most of the eigenvalues have negative real part, but some of the eigenvalues have 0 real part. So, none of the eigenvalue have real part in the right hand side of the S plane. So, if some of them are on the right hand side of the S plane, then it will be source or the system will be unstable. With this thing, so we know when the system will be stable, that means when the system response will be bounded, and unstable when the system response will be unbounded. So, from the trace and determinant also we can get the same thing. So, we know the saddle point. So, the saddle point will be here, and then so if you plot the determinant versus trace, so we can see this trace square equal to 4 into determinant. So, this curve we can plot. So, here it will be centers, unstable spiral, stable spiral. So, if it is in this region it will be stable spiral. So, in this region it will be stable nodes above this line. So, above this line it will be, on this line it is center and it is unstable spiral and unstable nodes. Nodes is imaginary part equal to 0. So, if the eigenvalue has 0 imaginary part, actually you will get that thing. Already we have plotted this thing and we have seen, and these are different examples also we have taken previously, and we know regarding the multiple branch in case multiple equilibrium solutions or multiple equilibrium points in case of the nonlinear system. And for these multiple equilibrium points, we must use this basin of attraction method to find for which equilibrium, for which initial points. So, one obtain which equilibrium points. So, for different, for example, you can see for all these initial points it is coming to this thing, and for all these initial point, so it is coming to A2. So, A1, A2. So, you can have bistable region here. So, if you draw a line here, so you can get the bistable region, and this in this bistable region. So, you can find this is one solution, bistable solution. So, bistable, but 3 solutions you have. So, out of this thing one is unstable. So, this point is the unstable saddle point. So, you can have a saddle point here. Now, let us revise this thing, this bifurcation. So, you have continuous bifurcation, discontinuous. So, you have static bifurcation, dynamic bifurcation. So, in case of static, so you have saddle node bifurcation, pitchfork or symmetry breaking bifurcation and transcritical bifurcation, and in case of dynamic, so you have this hop bifurcation. Okay. Already we have seen saddle. So, this is the saddle point and this is the saddle x double dot minus x equal to 0. So, you just see the roots of the eigenvalue or roots of this equation. So, x double dot minus x equal to 0. So, x double dot will be, or this auxiliary equation will be d square minus 1 equal to 0 or d square equal to 1. So, d equal to plus minus 1. So, the solution will be C1 e to the power t plus C2 e to the power minus t. So, the C1 e to the power t term will exponentially grow the response as t tends to infinite. So, that is why, so the response, so you can get, so one part will pull it up and the other part C1 C2 e to the power minus t. So, that will give rise to, so as t tends to infinity it tends to 0. So, this type of response are known as saddle. So, this is a saddle point. So, in the saddle you can, if you draw this x versus x dot, x versus x dot. So, you can see at a different region. So, the flow will be like this thing. So, the flow will be, so here the flow will going away. So, here the flow is this way, this direction, left side it is in, you just see in the left side it is moving in clockwise direction, in right side it is moving in anti-clockwise direction, and here in the top portion, here you just see it is moving in. So, it is moving in anti-clockwise direction and here it is moving in clockwise direction. So, similarly, so the stable node you can get x double dot plus 2 x dot plus x. So, this is similar to that of a this damped. So, this is that of a single degree of freedom system with damping. So, in case of damping, as t tends to infinite, the response tends to 0. So, it tends to, so all the response you just see, all the response to the left hand side is closing to this point, and similarly from right hand side also they are closing to the same point. So, all the in the phase portrait, so all of them are moving to the same point, and here, so this is a stable node point. So, similarly you have a center. So, in this case x double dot plus x equal to 0. So, the solution becomes x double dot minus x equal to 0. Here the auxiliary equation d square equal to minus 1. So, as d square equal to minus 1. So, d equal to plus minus I. So, the solution becomes a cos omega t plus b sin omega t. So, where this omega equal to 1 in this case. So, the response is harmonic. So, as the response is harmonic, if the displacement is written in terms of, for example, in sine, so the velocity will be in cos, and if you plot this displacement versus velocity, so it will be a circle only. So, x square plus y square will be equal to 1. So, this way, so it becomes a circle. So, this is a center, in this case this is a center and this is a, so in this case you can see that a stable spiral, you can get a stable spiral. So, it is spiraling down to, so this is a stable node. So, stable node means, so in this case, so you have, in this case you just see the auxiliary equation and you can verify, or you just find the roots. So, from the roots you can find that the roots are, so the roots will be a real root here. So, because you just see, so your equation becomes, what is the equation, d square plus 2d. So, here the equation is d square plus 2d, d square plus 2d plus 1. So, this is the auxiliary equation. So, it should be equal to 0. So, then this is d plus 1 whole square, d plus 1 whole square equal to 0. So, you have two roots and they are equal roots and the value is minus 1, roots are minus 1 and minus 1. So, these are real roots, only real roots, and they lie in the left hand side of the S plane. So, as they are lying in the left hand side of the S plane, the solution must be stable. So, this is a stable solution you are getting. So, it is a node. So, if you have imaginary parts, for example, in this case what is the auxiliary equation? Auxiliary equation, this is d square plus d square plus d plus 1. So, this is the thing. So, this should be equal to 0. So, the roots of this equation you can write, for example. So, d will be equal to minus b minus 1 plus minus b square minus 4ac by 2a, b square becomes 1 minus 4ac, this is 4 by 2a, that is 2. So, this becomes minus 1. So, here the root you just see, this becomes minus 3. So, inside this square root we have minus 3. So, it will be root 3i plus minus. So, it will be plus minus root 3i by 2. So, here it is imaginary. So, we have the imaginary root. So, if we have imaginary root, so the response will be oscillatory. So, that is why you are getting the spiraling of the solution. So, in this case it will not be spiral. So, it is a stable node, but in this case it will spiral down and finally it will be at 0. Finally, it will be at 0. Last class we have studied regarding the static bifurcation. So, we can have further discussion on the static and dynamic bifurcation today. Given a equation x dot equal to f x mu. So, you just see here we are using semicolon instead of comma, as mu is a parameter, that is why we are using the semicolon here. X is a variable, but mu is a parameter which we are varying or we are changing to get different response. For a given equation x dot equal to, so if we have a equation x dot equal to f x mu, x is the variable and mu is the parameter. So, for steady state or for equilibrium position or for fixed point position, so this x dot must be equal to 0. So, by equating this x dot equal to 0, so we can get all the fixed point response. So, after getting this fixed point response, so we can study whether the fixed point is stable or unstable, or there is some bifurcation points also. To have a bifurcation point, let for mu equal to mu c, mu critical value, let there is a bifurcation point. So, to find this bifurcation point, the first condition must be if x 0, let x 0 is the corresponding value. So, if x 0 mu c must be equal to 0. So, this is the first condition, and second condition, the Jacobian matrix, that is dxf, that is del f by del x, has a 0 eigenvalue while all other eigenvalues have non-zero real parts at x 0 at mu c. So, has a 0, so it must have a 0 eigenvalue. So, the Jacobian matrix dxf del f by del x has a 0 eigenvalue while all of its other eigenvalues have non-zero real parts at x 0 mu. Hence, this point is non-hyperbolic. Yes or no? At bifurcation point for a hyperbolic. So, in case of a hyperbolic fixed point, all the real parts of the roots must not be 0. So, it should be non-zero real part of the eigenvalue for hyperbolic fixed point, but if one of these eigenvalue is not 0, so then this becomes non-hyperbolic. So, for the static bifurcation, these two conditions must be satisfied. So, one f x 0 mu c equal to 0 and this Jacobian matrix must have a 0 eigenvalue. In case of dynamic bifurcation, so we can see, so it must have a eigenvalue, so which will have the imaginary parts also. So, already we have discussed regarding the saddle node bifurcation, and the in case of saddle node bifurcation, the generic form of this thing equal to mu minus x square, and so by putting this x dot equal to 0, so we have the fixed point equal to x square equal to root over mu. So, from that thing if you plot this x versus mu, so we have this curve. So, now if we can find the slope at each point, so you can see the slope at this bifurcation point. So, before mu equal to 0, so all the points mu less than 0. So, root over mu is imaginary. So, it is not real, that is why the solution does not exist. Solution does not exist before mu equal to 0. So, after mu equal to 0, we have two solutions. So, out of these two solutions, the upper branch you can see, so it is stable because its eigenvalue will be negative and the lower part is unstable. So, if you plot the slope at each point, so you can see at this bifurcation point or at this point they have the same tangent. So, saddle node bifurcation as the two branches meeting at mu equal to 0 have the same tangent. So, here also by taking some other examples, so you can see, so these so we have a saddle node bifurcation point here. So, it is not here. So, we have a saddle node bifurcation point here and also one saddle node bifurcation point here. In this case, further you can construct a matrix, that is dxf and f mu matrix. So, where f mu equal to del f by del mu and dxf is nothing but the Jacobian matrix, and you just construct a matrix with the Jacobian matrix and f mu, and in this particular case. So, in this particular case, for example, this is f equal to mu minus x square, f equal to, so as our f equal to f x equal to mu minus x square. So, our dxf, so if you differentiate this thing with respect to x, dfx equal to minus 2x and f mu equal to f mu, you differentiate this thing with respect to mu. So, this becomes 1. So, if I will construct a matrix, so for the equilibrium position, so for the equilibrium position dxf equal to 0, so this part equal to 0 and f mu equal to 1. So, we have a matrix now, we have constructed a matrix, that is dfx, dxf, dxf and f mu. So, this matrix equal to 0 and 1 in this particular case. So, here you can see this f mu does not belongs to the range of dfx. So, rank of this matrix is 1. The origin of the saddle node bifurcation point. So, the origin of the this is the, so the origin is the, so at x equal to 0. So, this origin is a bifurcation point. So, here at this point it satisfies both the conditions and at the same times. So, to distinguish the saddle node bifurcation point with other different static bifurcation point, you must have to do this test. Just find the rank of this matrix. So, this rank you can see in this case. So, the rank of this matrix is 1. This origin is a saddle node bifurcation point. So, we will see in other cases at a saddle node point f mu does not belong to the range of f mu. So, here f mu equal to 1. So, this does not belong to the range of dxf. So, in case of dxf, so you have only 0, and for pitchfork and transcritical bifurcation point f mu belongs to the range of dxf. So, we can see later in this example with the example for this pitchfork and transcritical bifurcation. So, we will construct this matrix and check. So, what is the range of this matrix? So, it may be noted that the range of an n cross n matrix A consists of all vectors A z, where z belongs to R to the power n. Hence, dxf f mu has rank of n at saddle node bifurcation point. In this previous case, so it has a rank of 1 at the saddle node bifurcation point and the rank of n minus 1 at other static bifurcation point. So, if you take other static bifurcation point, so you can find the rank is less than 1. So, that is n minus 1. This point has to be remembered, or this point has to be taken care while distinguishing between the saddle node bifurcation point, transcritical bifurcation point and this pitchfork bifurcation point. Particularly from the shape also we can decide that thing. So, in case of a saddle node bifurcation point at the saddle point, so the two branches are the meeting point of the two branches. So, they will have the same tangent, but in case of pitchfork bifurcation, from the shape itself it can be known that this is pitchfork. So, it is starting, so like a pitchfork. So, pitchfork we know. So, this is the pitchfork type of bifurcation, and here also the generic form is mu x minus x q. So, x dot equal to mu x minus x q. So, in that case let us see. So, x dot equal to f x mu. So, it is equal to mu x minus x q. So, by putting this x dot equal to 0. So, we will get the equilibrium position. So, mu x minus x q equal to 0. So, by taking this x common, so x into mu minus x square equal to 0. So, x equal to 0 is an equilibrium point, and also x square equal to mu is also an equilibrium point. So, you have three equilibrium points, one is x equal to 0 and other one plus minus root over mu will be another two equilibrium points. By plotting these things, we can plot O to A, that is equal to 0, O B also A to B the trivial state, that is x equal to 0, and this non-trivial state. So, this is mu versus x, you can plot mu versus x, you can, this is x, this is mu, x axis y x axis is mu, x axis is mu and y axis is x. So, by plotting this thing, so now you can see the Jacobian matrix. So, differentiating this thing mu x minus x q. So, we will get the Jacobian matrix. So, this becomes mu minus 3 x square. So, for the trivial state, so we can find this A minus lambda I. So, we can do A minus lambda I. So, in this case, so A is the Jacobian matrix or J minus lambda I. So, this becomes mu minus 3 x square minus lambda, making this thing equal to 0. So, we will get lambda equal to mu minus 3 x square. So, mu minus 3 x square is the, so mu minus 3 x square. So, for trivial state as x equal to 0, so lambda equal to mu. So, for trivial state, so this is the trivial state. So, here x equal to trivial state, x equal to 0. So, as x equal to 0, so we have lambda equal to mu. So, for non-trivial state, now lambda equal to mu minus 3 x square. So, by putting different value of, already we have this x square equal to mu, x equal to plus minus root over mu. So, x square equal to mu. So, by putting this thing, so we can have mu minus 3 mu, this is minus 2 mu. So, you can check for non-trivial branch. So, the lambda, that is the eigenvalue, becomes minus 2 mu. Now, by putting this different value of mu, so we can find whether the system is stable or unstable. Here up from A to O, so from A to O, so that is mu less than, so this is mu value. So, for mu less than 0, so if mu less than 0 for the trivial branch, so mu is negative. So, this part mu equal to negative. So, eigenvalue is negative, that is why this is stable. And for O to B branch, so mu is positive. So, as mu is positive, lambda is positive. So, from this equation lambda is positive. So, as lambda is positive, the response is unstable. So, the system is unstable. So, now for the other two branches, let us see. So, this becomes minus 2 mu as to the right hand side for this non-trivial branch, mu is always positive. So, minus 2 mu is always negative. So, this branch and this branch, so both the branches are then stable. This type of bifurcation, so from where, so it is moving from a stable trivial state to stable non-trivial state is known as supercritical pitchfork bifurcation. So, this is supercritical pitchfork bifurcation. In this case mu x minus x q. So, this is supercritical pitchfork bifurcation. Similarly, we can see here again you just see you can check by constructing this d f x and f mu. So, what is f mu in this case? So, f mu, so find f mu. So, if you differentiate this with respect to mu, so you will get f mu equal to x, yes or no. So, f mu equal to x. So, for the trivial state x equal to 0, so f mu equal to 0, already dxf equal to 0. So, it has a rank of, so this becomes 0 and this becomes 0. So, this is 0 0. So, the rank becomes 0. So, this rank is not 1 here. So, the rank as we have seen there. So, rank is n minus 1. So, in this case, so we can differentiate or from this thing from the saddle node bifurcation point from or by constructing these df, dxf and f mu matrix. Now, you just take the other one, that is x dot equal to f x mu, but you take x dot equal to mu x plus x q. So, previously we have taken mu x minus x q. So, here it is mu x plus x q. So, if you take mu x plus x q, so then x dot equal to 0. So, x dot equal, putting x dot equal to 0. So, we have this, taking this x common. So, x into mu plus x square equal to 0. So, x equal to 0 is one solution and the other solution becomes x equal to plus minus root over minus mu. So, this is the other two solutions. So, we have three solutions here, and if you can plot it, so we can see this one. Similarly, for trivial state, so for trivial branch, let us find the Jacobian matrix. So, Jacobian matrix, from the Jacobian matrix. So, differentiating this thing with respect to x. So, the Jacobian matrix you will get mu plus 3 x square. So, for trivial state, by putting these x equal to 0. So, lambda becomes lambda equal to mu. So, lambda equal to mu for the trivial state, and here mu less than 0. So, this branch is stable, and mu greater than 0. So, this branch is unstable. Similarly, for the non-trivial state, our lambda becomes minus 2 mu, lambda becomes minus 2 mu, but in this case this mu is negative, minus 2 mu is positive. So, minus 2 mu is positive as lambda is positive, that is the eigenvalue is positive. So, these branches are unstable. So, this is unstable branch. So, here that means the stable and unstable branch. So, this one non-trivial stable and two non-trivial unstable leads to this unstable branch after the bifurcation. So, already we know a bifurcation point, at bifurcation point either it changes, the response changes qualitatively or quantitatively. So, in this case these three branches merge to have a single branch. So, that is a number. So, the number is changing. So, that is why it is a bifurcation point. Also the stability, type of stability is also changing. So, here as the resulting response is unstable, previously we have a stable branch and two unstable branch. Now, this becomes completely unstable. So, this is known as subcritical pitchfork bifurcation, which is a dangerous bifurcation, because after this thing, as there is no solution available, the system response may jump to infinite and the system may tends to an unstable region, or it may be if the system may get damaged. So, let us see the Hopf bifurcation. This is the dynamic bifurcation. So, in case of the dynamic bifurcation, so we have this f x mu x 0 mu c must be equal to 0. This is the first condition, and the second condition is the Jacobian matrix d x f, that is del f by del x, has a pair of purely imaginary eigenvalues. So, it must, you just see the real part is 0, but it must have a pair of imaginary eigenvalues, that is plus minus I omega. So, it will have plus minus I omega, while all of its other eigenvalues have non-zero real parts at x 0 mu c. Hence, the point is a non-hyperbolic fixed point. The third point is for mu equal to mu c, let the analytical continuation of the pair of imaginary eigenvalues be lambda plus minus I omega. Then del lambda by del mu not equal to 0 at mu equal to mu c. So, this condition is known as the transversality condition, as the eigenvalues crosses the imaginary axis with non-zero speed. As they are crossing the imaginary axis with non-zero speed, so it will give rise to periodic response. So, when all the above three conditions are satisfied, a periodic solution of period 2 pi by omega is developed at x 0 mu c. Such bifurcations are called Hopf bifurcation or Poincare-Andronov-Hopf bifurcation. So, this is Hopf bifurcation. So, in case of Hopf bifurcation, so from the fixed point response we are getting the periodic response. So, if from a stable fixed point we are getting stable periodic response, then it will be known as supercritical Hopf bifurcation, and in case of subcritical Hopf bifurcation from a unstable fixed point. So, we are getting a stable fixed point along with a periodic response. We can have supercritical or subcritical Hopf bifurcation points. So, the generic form of the Hopf bifurcation can be written in this way: x dot equal to mu x minus omega y plus alpha x minus beta y into x square plus y square, y dot equal to mu x minus omega y plus alpha x minus beta y into x square plus y square. Now, by making this thing equal to 0, so we can get the equilibrium conditions or equilibrium points and or the fixed points, and finding the eigenvalue. So, we can see how by changing the system parameter mu, how the eigenvalue are behaving. So, we can see at the critical point. So, it is crossing the imaginary axis with non-zero imaginary parts. So, if they are crossing the imaginary axis with non-zero imaginary or non-zero imaginary parts, then we are going to get the Hopf bifurcation. So, we will see different examples later how this all these types of bifurcations are occurring in real systems. So, these are some of the examples also you can take. So, where it leads to chaotic response. So, you can see some of the experiments also can be conducted to study all these system. For example, let us take a beam. So, this beam can be vibrated to see the response. So, some of the response it is. So, by putting this accelerometer or by putting this oscilloscope, you can also check the vibration of the system. In addition to Duffing equation what you have seen before, so we can have different other type of Duffing equation. So, here is one Duffing equation with fractional order derivative. So, here this additional term you can see. So, that is known as the fractional order. So, you can study many different type of Duffing equations and their response, and which will lead to many different type of bifurcation points also. So, with this thing we will close this class today, and we will study the periodic response which generally occur in case of a parametrically excited system. So, we have finished the finished the forced vibration or direct excitation system, directly excited systems. Next class we will see the systems which are parametrically excited. Thank you very much.